My name is James Reynolds. On behalf of my colleagues at North Carolina State University in the departments of Electrical and Computer Engineering, as well as Crop and Soil Sciences, I would like to present our latest developments in the agricultural sensor space. To begin with, I'm going to be talking about how we collect data for precision agriculture and phenotyping and how the development of low-cost sensors could revolutionize these two fields. Finally, I'll conclude with looking at a new bioimpedance metric for quantifying physiological changes that I think could have a great impact on precision agriculture and phenotyping. First question you might ask, though, is why do we want to deploy sensors in fields? We have UAVs, we have satellite imagery, as well as other techniques now that can help us with phenotyping and precision agriculture. I think there's three specific areas that field-deployed sensors have an advantage. First, there's certain fine peculiarities that you can only get in the field. So, for instance, if you want to get soil moisture, you will need to be in the field for that. Temperature and humidity, you can only get specifically relative to the plant on the ground beside it. Second aspect is that a lot of our remote sensing methods currently are limited by the weather, and so with field-deployed sensors we can understand what's happening in real time and in that specific location regardless of whether the weather is positive or negative. With precision agriculture, these are relevant because it allows for the specific application of resources in a wise and conservative manner. And with phenotyping, the additional data helps us better understand the various effects on the expressions. When my colleagues and I started out in this field, we were looking for a system that our sensors would be able to be integrated into. We were also looking for a system that was cheap enough that we could have large-scale deployment for farmers. What we found, though, was neither an open system that could be added onto, neither was there a system that was at low enough cost that we could get the metrics we were looking for cheap enough. And so we started the journey of creating our own system. Along the way, we found several details that I think are helpful for the community at large to understand, especially with the onset of the Internet of Things, so that more researchers and more companies can get into this space and provide lower cost systems for farmers and scientists alike. Our system is housed within a commercial enclosure with venting to allow for airflow to pass through it. There can be 1 or 2 2.5 watt solar panels on top of the system to allow for charging and powering the system throughout the day. But at night, the battery provides power. It's a 1600 milliamp hour battery. The charging and regulation is taken care of on the main board that also includes a LoRa transceiver as well as an ARM microprocessor. This collects the data from the various front ends. Altogether, the system has a size of 26 centimeters by 15 centimeters by 18 centimeters. The peak power draw is 740 milliwatts when transmitting via the radio, but this only happens for a few seconds. When doing measurements, the power draw peaks at 112 milliwatts, and at idle, it consumes 41 milliwatts. The first sensor we're going to look at is the light quantity sensor. The issue with taking an off-the-shelf chip for human use is that human eyesight is sensitive to different wavelengths than that of plant photosynthesis. However, this can be easily accounted for by using fixed conversion ratios given a known light source. Considering that this is for outdoor use, sunlight is well characterized and is easily converted between lux to photosynthetic photon flux density. You can see the sensor on the right. It uses the SI1133, and it's housed within a custom 3D printed base. This base has an O-ring on top of it, and then a Pyrex watch glass secured on top of it. This allows all of the relevant wavelengths through to the sensor, as well as recesses the sensor. The diffuser is not shown here for clarity. Shown here is the difference in output between our sensor and that of a commercial sensor, the Light Scout. As you can see, with the diffuser, as is properly implemented, there's only a 3.3% difference. Without the diffuser, however, the difference expands to 12%. The diffuser is important because it accounts for the variety of angles, in this case 12 to 58 degrees, as well as the variety of intensity of lights. This 3.3% difference is within the bounds of the difference between various commercial sensors. The second sensor is the soil moisture sensors. In this case, our system can use either the commercial Echo EC5 shown on the left or an open source design shown on the right. These two have different geometries as well as frequencies of measurement that show up in the data. The advantage to the open source, though, is that it can measure light values as well as the temperature of the soil, and it can do so at 1/10 of the cost. An important aspect of soil moisture sensors is that they need to be calibrated. The calibrations for our sensors are shown on the top, with A being the open source sensor and B being the commercial sensor. We found that the two had differing responses. Although the correlation between the two was 0.9 over the course of 2 weeks of measuring the soil moisture beside a mature maize plant, the open source sensor had an average volumetric water content of 0.1 meters cubed per meters cubed, compared to the average of the commercial sensor at 0.21. The minimum for the open source was 0.03, the maximum was 0.43, the minimum for the commercial sensor was 0.01, and the maximum was 0.41. We're unsure if these differences are a matter of reliability, or if there's an actual difference in the gradient between the soils. The final sensor is the bioimpedance analyzer. I have it configured for a 2-electrode measurement of plant tissue, where electricity is run through the tissue and we characterize its properties via the response. The implementation is fairly straightforward with Analog Devices 5941. This chip allows for a small but powerful implementation that uses low power and can measure a wide range of impedances. For comparison's sake, we have our implementation measuring an RC circuit alongside a commercial device, the PalmSense 4. There was a 2.2% difference, which corresponded to 4.9 kiloohms. Given the amount of noise on the PalmSense 4, this seemed perfectly acceptable. Why do bioimpedance measurements matter, though? Shown here are some measurements in the vascular system of the plant, and as you can see with the banana and sugarcane, water movement due to watering shows up in bioimpedance. With pygmy palm and soybean, we saw unique diurnal patterns that seem to match with sap flow in the plants. Realizing that there was a connection between the water status of the plant and bioimpedance, we conducted an experiment where we wrapped soybean plant pots in plastic to inhibit water loss to transpiration only. We had 3 of the plants serve as well-watered controls, and the other 3 served as drought specimens where they lost 70 grams of water as measured by weight per day. The bioimpedance shown in the graph above increased for the drought group by 234% after the water was withheld from it. This is 725 kiloohms higher over the control plants, which is significantly different by a p-value of 0.032. The environmental parameters are shown in the graph below. A key takeaway is that the bioimpedance rapidly increases and is sensitive to water values. This is important because it can predicate the wilting, and so we can actually have a prior warning before a plant shows any visible signs. This has many different applications, but most importantly, it tells us exactly at what point a plant will respond to differing water values. Currently, we don't have an exact knowledge of when plants are permanently affected by low volumetric water content, but with this methodology, we could determine exactly when a plant will start to respond to low water values. In conclusion, I've demonstrated that it is possible to reduce the cost of the sensors and the overall system. In this case, with the open source soil moisture sensor, the overall material cost is around $150 US. Given the mass manufacture of the system, this cost could be reduced. However, there is a trade-off in regards to quality and reliability. As shown, the open source soil moisture sensor doesn't quite give the same response as the commercial soil moisture sensor, and there is considerations that need to be taken as to what the application of the system is going to be. In this case, though, we've shown that it is possible to have the accuracy needed with these sensors to make critical decisions for precision agriculture. Finally, bioimpedance looks like it could be an important indicator of drought stress in plants, and we posit that it could be an integral part of future systems. This research would not have been possible without the support of the United States Department of Agriculture and the King Abdullah University of Science and Technology. I welcome your questions as we seek to explore and improve precision agriculture and phenotyping.